How are you, all of you? I hope you are fine. Okay, have you seen the previous videos? What I have uploaded in my channel? Thank you. Let's start today's class. In today's class, we will start about inductors. What do you know about inductors? In this session, we will see about how an inductor stores energy, how it will store energy, and inductance, types of inductor, and how can we connect inductors. That means like that of capacitors and resistors. Inductors also can be connected in series, in parallel, or combination. So how can we find the effective inductance of different connections of inductors. What is inductor? What is inductor? An inductor is a passive electrical component formed by a coil of wire that exhibits the property of inductance. When a length of wire is formed into a coil, it becomes an inductor. A coil, if it is when a long coil is formed in the form of a coil, it becomes an inductor. Current through the coil produce an electromagnetic field due to Faraday's law. If the current carrying conductor will induce an electromagnetic field, especially if it is a varying, that means AC alternating current. The magnetic lines of force around each loop or turn in the winding of the coil effectively adds to lines of force around the adjoining loops, forming a stronger magnetic field within around the coil. As you can see here, around the coil, and it will act like a magnet. The net direction of the total magnetic field creates a north and south pole. As you can see here from this figure, it will create like north and south pole like that of a magnet due to if the current is passed through this coil. When there is a current through an inductor, an electromagnetic field is established. If the current changes, the electromagnetic field will also change. Sorry for the disturbance. An increase in current expands the field, and decrease in current reduces the field. If the current is increased, the field will expand, and if the current is decreased, the field will reduce. Therefore, a changing current produces a changing electromagnetic field around the inductor. In turn, the changing electromagnetic field causes an induced voltage across the coil in the direction of opposite changing current. Due to electromagnetic induction by Faraday's law, if there is a changing current in the coil, electromagnetic force or a voltage will be induced in that coil. Electromagnetic force or a voltage will be induced in that coil. The property of such a material is called self-inductance, but usually referred to as simply an inductance, and we can symbolize by a capital letter L. It can be symbolized by a capital letter L. What does mean inductance? Inductance is a measure of a coil's ability to establish an induced voltage as a result of a change in its current, and that induced voltage is in the direction to oppose that changing current. The direction of the induced voltage will be determined by Lenz's law, a scientist who determines the induced voltage direction or sign. What is the unit of inductance? If you remember from the previous class, the unit of resistance is what? Oh, like that. The unit of inductance is Henry, symbolized by H, and is a basic unit of inductance. This is the basic unit of inductance. By definition, we may define a Henry. The inductance of a coil is 1 Henry when a current through the coil changing at the rate of 1 ampere per second induce 1 volt across the coil. As we have already said, if there is a change in current, due to that changing current, electromagnetic field will be induced, and that changing magnetic field will induce a voltage. So this is what we call Faraday's law of induction. This is Henry, a scientist who was between 1797 and 1878, and he have influenced. He is a scientist, and he have introduced especially related to the inductance of your materials. Inductance of your materials. How an inductor will store energy? How an inductor will store energy? If you remember, in the previous class, a capacitor will store energy in the form of what? In the form of electric field. But when you come here, an inductor will will store energy in the form of magnetic field. In the form of magnetic field. An inductor is a passive element designed to store energy in a magnetic field, while a capacitor stores energy in electric field. An inductor stores energy in a magnetic field created by the current. The energy stored is expressed as 1 over 2 Li square. 1 over 2 Li square here. This is the equation which expresses the stored energy in the inductor. Where I is the current in ampere and L is the inductance in henries and W is the energy stored in joules. The energy stored in joules. So this is the relation which indicates the energy storage in an inductor or a coil. What is the physical characteristics of an inductor? Physically, as we have already mentioned, an inductor is a coil. Yes, an inductor is a coil. So what are the physical characteristics? The physical characteristics of an inductor. The physical characteristics are important in establishing the inductance of a coil. The permeability of the core material, the number of turns of the wire, the core length, and the cross-sectional area of the core. These are the physical characteristics of an inductor. Let's see the first one, that is the core material. The core material. That means the coils which will be wounded into that core material or the core. If you remember from your introduction to machine course, when we talk about transformers, the transformers have a core, yes, which the windings will be wounded into it. So that core may be made up from different materials like that. Here in an inductor, a core is also there. An inductor is basically a coil of wire. The material around which a coil is formed is called the core. The material around which the coil is formed is called the core. Coils are wound on either on a non-magnetic, like air, wood, plastic, glass. These are non-magnetic, or it may be magnetic, like iron, nickel, steel, cobalt, etc. Magnetic materials have permeabilities that are hundreds or thousands of times greater than that of vacuum and are classified as ferromagnetic. They are classified as ferromagnetic. A ferromagnetic core provides a lower reluctance. Reluctance is similar to that of a resistance in a current in electric field, but here in a magnetic field, this reluctance is related to a resistance. If the resistance is lower, the current can easily flow like that. The flux in the magnetic circuit, if the reluctance of a material is small, the flux can be easily flow inside that magnetic material. So this ferromagnetic core provides a lower reluctance path for a magnetic lines of force or the flux, and thus permits a stronger magnetic field. It can permit a stronger magnetic field. The permeability of a core material determines how easily a magnetic field can be established. This permeability indicates. The inductance is directly proportional to the permeability of the core material. As we have already mentioned, the material at which the coil will be wounded is called what? The core. So the inductance is directly proportional to the permeability of the core material. Let's see another physical parameters. That is the number of turns of the wire, the length, the cross-sectional area of the core are factors in setting the value of the inductance. The inductance is, by definition or by derivation, inversely proportional to the length of the core and directly proportional to the cross-sectional area. Also, inductance is directly related to the number of terms square here, as you can see here in this equation. L is the inductance, which is equal to n square. Mu naught is the permeability of the material, that means the core material especially, and A is the area, and L is the length. Let's show you. Here it is. L means this is the length. This is the length of the winding. And this is the core material, and the cross-sectional area is this one. This one is the cross-sectional area, and this is indicates the number of turns. So the inductance of an inductor can be calculated by using this formula, that is n square mu A over L. Mu is the permeability of the material, and A is the area. This is the area. And L is the length at which the inductor coil is wounded. The length at which the inductor coil is wounded. So this is the general equation which indicates the inductance of an inductor. And if the material is not air, we may use this one. Mu naught is the permeability of the air. And its value is 4 pi times 10 to the power of -7 Henry per meter. N is number of turns, L is length, A is the cross-sectional area, and mu is the permeability of the core. Don't forget that in these two things, the first one is the amount of voltage induced in a coil is directly proportional to the rate of change of the magnetic field with respect to the coil. The amount of voltage induced in a coil is directly proportional to the rate of change of the magnetic field with respect to the coil. This is Faraday's law of induction. And how can we determine the direction? By Lenz's law. When a current through a coil changes and an induced voltage is created as a result of the changing magnetic field, the direction of the induced voltage is such that it always opposes the changing current. So we can determine in this way. What type of inductors do you know? Like that of a capacitors and resistors, inductors are different types of inductors are there. Inductors are classified according to the type of core material. Basically, they fall into two general categories, that is fixed and variable. Both fixed and variable inductors can be classified according to the type of core material. There are three common types. The first one is we may use air as a core material. That means nothing. Only the air will be filled inside the core. And the other one, the iron we may use, and we may use a ferrite core. In adjustable or in variable inductors, usually have a screw type adjustment that moves sliding core in and out, thus changing the inductance. As you remember, the inductance of inductor is related with its length of the winding. So by using this screw drive, we can adjust the length. So the inductor will be variable. The inductance of the inductor will be varied. Some fixed inductors are usually encapsulated in an insulating material that protects the fine wires in the coil. To avoid the breaking of the fine wires, we will encapsulate it by protective things. Encapsulating inductors have an appearance similar to a small resistor. It may seem like a small resistor, but for the sake of protection, it is encapsulated by a protective component, but inside there is a coil still. Physically, inductors seems like this one. As you can see here, especially this small one, it seems like a resistor, but it is encapsulated. Not a resistor. This is an inductor. And the other type is this one. This one is especially a variable type. By using this screw, we can adjust the values. And this is the symbol for air core inductor, and this is the symbol for iron core inductor, and this is the symbol for ferrite core inductors. And this indicates like that of a resistor, it is a variable type inductor. This is a variable type inductor. The other very important issue is flux in inductors. What is flux? Do you know flux? The relation between the flux, the current, and the inductance of a material. The inductance of a material. The relation between the flux in inductor and the current through the inductor is given like here. This is the relation. Phi which is equal to Li. This is the flux is directly proportional to the inductance and the current, like this one, the current. An inductor consists of a coil of conducting wire. A coil of conducting wire, as I have already mentioned, this is a coil of conducting wire. So the voltage is related by a Faraday's law. The induced voltage in the inductor is directly proportional to the change in flux per time, or the magnetic field change in magnetic field. That means which is equal to L times di by dt, because the induced flux or the magnetic field is created by the current flow. So it is directly proportional to like this one. So what does it mean physically? What does it mean physically? If we relate the equations, these two equations, that is V which is equal to d phi by dt, this is the flux induced in the coil, and this is the current. So what does it mean physically? This change means when the current through an inductor is constant, so there is no any induced voltages, so the voltage across the inductor will be zero. There is no change, the same as a short circuit. So in DC circuit, the inductor will act like a short circuit. No abrupt change of current through an inductor is possible except in an infinite voltage across the inductor is applied. The inductor can be used to generate a high voltage, for example, used in ignition element, during ignition. That means by varying the change, we can increase the induced voltage by varying the change within a short period of time. So there is a chance to generate a high voltage in an inductor. Uh, an inductor are like a short circuit to DC, as I have already mentioned. A short circuit. The current through an inductor can't change instantaneously. It can't change instantaneously, especially in AC. That means if it is DC, it will be constant. So no issue. But when we connect our inductor into AC circuit, the current will not instantly change, but rather it will smoothly change. No instant change in the inductors. The current will not instantly change. So this relation indicates what I have already mentioned. The energy storage I have already talked. So anyway, as you know, power means what? V times I. Yes, V times I. We know it. It is very well. So, and the voltage is L di by dt times I. So if we integrate, we'll arrive this derivation. So I already mentioned 1 over 2 times Li square. This is the energy stored in an inductor. The energy stored in an inductor in the form of what? In the form of magnetic field. Okay. Right now we are at the position to talk about the connection of inductors, different connections, series, parallel, and series parallel connections. So when inductors are connected in series, the total inductance increases like that of resistors. Connected in parallel, the total inductance decreases like that of resistors. This calculation for total inductance is in parallel is analogous to calculation of total parallel resistance and total series capacitance. This is similar like that. If you remember, the calculation of capacitors and resistors in series and parallel connection is not the same, but here the series and parallel connection of inductance and resistors are the same. For series parallel combination of inductors determines the total inductance in the same way as total resistance in series parallel resistive circuits. So determining, if you remember, the calculation of resistors connection, it is similar. So we can add easily. And like that, the voltage will be divided in the series circuit. In the series circuit. So as you can see here, the total voltage is here V1, V2, V3. This is the inductors which are connected in series. So we can easily get the equivalent. The equivalent. Inductors in parallel, the same to that of resistors in parallel. The same to that of resistors in parallel. Resistors in parallel. So by applying KVL for the series connection of the previous circuit, we can easily get V which is equal to V1 plus V2 plus V3 up to Vn, and we know that the current in series circuit is the same. Yes, the current in series circuit is the same, so we can come up with in common di. So this indicates that the equivalent resistance, I mean impedance, that means impedance of an inductance is the summation. The summation. This is all about today's class. Thank you very much for your attention. If you have any question or doubt, you can put your questions in the comment box. See you in the next video.